I'm Bob.
I'm Kelly.
I'm Rafsan. Our project is to design a low-cost device that can separate protein-rich plasma from blood and use that sample to measure the osmotic pressure, analyze the osmotic pressure, so we can determine a heart attack. Heart attacks occur normally when blood flow to the heart is decreased as a result of a blockage of the arteries, which leads to a blood clot. The blockage of the arteries can lead to a decreased flow of oxygen to the heart, which will cause the heart to go into anaerobic metabolism, which would result into the generation of superoxide. And when the works are generated, the plasma has a higher binding affinity for these metals, and it would change the end terminus of the protein, resulting into the ischemia modified protein. Albumin. These are the models, the protein models. This is one without the end terminus where it's been modified, and that's with the end terminus before the modification.
And for testing for ischemia modified albumin, generally we would have to go to the ER and get triaged, and they would check for ischemia modified albumin by doing one of the 3 tests listed, which include albumin cobalt binding assay, which it's able to bind to ischemia modified albumin because of the affinity to bind to metal ions, and it's also really expensive and time consuming if we have to go get triaged at the ER. And a potential new alternative would be to measure osmotic pressure of a protein-rich plasma stream, which we're able to detect ischemia modified albumin at if it's present after a heart attack. And in the graph shown, there's just different fragmentation percentages of albumin in these, the osmotic pressure differences that are measured with about 20 psi at a set concentration of about a little over, maybe about 430 grams per liter of concentration of BSA. And note the higher concentration of osmotic, the increased osmotic pressure, which would show that we can use osmotic pressure to see if somebody has been suffering from a heart attack. And the potential new alternative would be to use a concentrating osmometer, which would help reduce our costs because it's integrated with the separation process. It would allow these devices to be implemented into convalescent homes and different ERs or hospitals. And the focus of our project in particular would be automating the delivery to the osmometer, which would be automating the protein feeds right here into the osmometer to detect osmotic pressure. And separation processes have been done before for plasma and blood separation through a 2-step method, and it has been proven that automated processes for separation do work, and they can be used to separate albumin for the process of diagnosis and treatment of autoimmune diseases. And in the same design, we're able to still use hollow fiber membranes and to separate or end up with the albumin as our end product. And this is just a schematic diagram which we drew influence from for our device.
Okay, so we had many project goals. First one was to successfully separate the protein-rich plasma from blood by separating out the 550,000 species or higher from our filtered sample. We needed to also extract 2 milliliters at least of protein-rich plasma to feed into the device, and this has to be delivered into the device that's going to measure the osmotic pressure. This all had to be automated. We wanted to make it automated and relatively cheap. The first proposed device that we came up with, the preliminary device, used multiple syringe pumps and membranes. However, we quickly realized that this was too expensive. The syringe pumps alone would cost well over $1,000. And so we had to redesign. And this is what we ended up with. We ended up with just using one hollow fiber membrane and utilizing two motors to move fluid through the system, and a microcontroller as the brains of our system. Here we have these two syringes on the outside. The two syringes on the outside move fluid through this hollow fiber membrane, and as the fluid moves through, it slowly, the smaller species and particles move through here to this one-way check valve where it gets trapped and sent into this syringe where we collect our sample. When we get enough sample, more than 2 milliliters, we're able to push the fluid through. This relay is activated, which opens up this two-way solenoid valve, and there we're able to deliver our sample into our measuring device, or what would be the measuring device.
So here's an example of a proposed filtration technique. So you can see that there's the inlet right there, and we'll inlet syringe, and we have the retention syringe. So upon continuous pumping, we get the collection of the filtrate, collection of our protein sample into the filtrate collection chute. So now let's zoom in to our the hollow fiber membrane. So we can see what happens in hollow fiber membrane is that it has small pores. So particles that are in a smaller size, like the blue ones, they're going to ooze out the membrane. And the bigger size, the red ones, are going to stay inside the hollow fiber membrane. So now that was our hollow fiber membrane. So another functional blocker for our device is the proposed the syringe pump mechanism. And a motor one is placed underneath a motor tube, so it goes from inlet to the retention syringe. So next we have the way that our system does is basically pushes the push plate pushes the syringe into the inlet, and it moves towards the right, towards the retention flow syringe, and pushes the plate. And this is a continuous process. So upon this, we're able to collect our protein sample in the filtration collection. So you may be wondering what type of sample we used. We used a bovine milk sample. So let's go over some data on that. So they're about like 30 to 35 grams of protein. It has about 33.6% of fat, 4.6% of lactose, etc. So our membrane has a nominal molecular cutoff of 5,000 Dalton. And what happens is that particles that are a size more than 500,000 Dalton, they're going to stay inside the membrane, and particles that are below the 500,000 Dalton, they're going to ooze out the membrane. Some of the examples are serum proteins, a BSA sample, etc. And Jonatan is going to explain
Here's a video, a short video, a sped up version, since ours takes a while. And there you see the first syringe being pushed in, moves to the second position, and there pushes that one. This process will happen multiple times in order to accumulate our sample in here. Here we have an inside view. We have milk going into here, and over there the other syringe being pushed out, and the filtrate or slowly being collected here. It takes a while, but you'll slowly see the syringe plungers move back as we collect that sample. This is what we ended up with. As you can see, the difference in our non-filtered sample here at the bottom and our filtered sample after we remove the particles which are 500 kilograms higher. And that's what we ended up with. We did some calculations to check the efficiency of our motors. So the first motor, we ended up with an efficiency of about 90%. Our second motor, we had an efficiency of 81 without the load, and then once we added fluid into the syringe, we ended up with a 63% efficiency.
Now, to account for the jet volume, the amount of the filter that stays in the tubes, because we used like a couple of tubes just to collect the filter, we estimated like the different lengths of the tubes for about 30 centimeters and then 11. And you can see the shorter the tubing goes, the less get blood into the tubes. And these are our results for the separation. We ran 6 samples with each time duration starting with about 30 minutes, and then the longest one was about 111 minutes. Our target was to get 2 milliliters for that would be the osmometer for the milk pressure reading. And we got it at around 30 minutes, which actually made our goal. And you can see that the graphs as the time goes on, the frequency increases as well.
And this is an economic summary of our device. As you can see, we significantly decreased the price. Major components are big ticket items, or the micro-cost follow fiber membrane, which costs around $100. The stepper motors, which are about $64, and then the brains, which is the Arduino microcontroller, that's actually pretty cheap, only about $30. The total cost came out to be about $500, significantly less.
And future work for the device would include improving the separation by having a cascade separation process, which would involve the use of a 500 and 100 kilodalton size core size for the hollow fiber membrane. And we also want to look at decreasing separation time. So we want to be able to obtain 2 milliliters of sample in less than maybe 30 minutes, so that their readings can be faster than, or the readings can be more efficient, or the process can be more efficient. And we also want to improve the delivery of the plasma feed, or the protein feed into the concentrated osmotic. And here are the following people with electro knowledge for helping us throughout our senior design project.
We're doing a little demonstration. Fine. Plunger is going to be moved in as the push plate moves forward. It just takes a while. That's why we had this sped up video. You guys don't have to suffer through it. If anybody has any questions while we wait.
Any questions? So what's the size of a blood sample versus an IV?
What we used for the bovine milk was a 10 milliliter sample for a 10 milliliter syringe, because the inserts for our device are designed to fit 10 to 20. And with that, we already saw that we were able to obtain, over a span of 115 minutes, a roughly 7 milliliter sample separation, which is an increase from what we wanted. So if assuming that the protein levels in humans is less than that in the whole milk that we use, if it is, then we probably only need to use the same amount of sample, same 10 milliliter sample size to obtain what we want. Maybe 2 milliliter sample, but an increased amount of time, so maybe about 45 minutes to get a 2 ml sample.
Did you guys ever analyze your filtrate to see if you in fact had proteins and what concentration they were in?
No, we didn't.
You just stopped it.
What's the separation do? Have you measured what's the recovery rate?
Oh yeah, we did. For the membranes were estimate of they are from the company. They made the estimate to have about an 85% recovery. But then we did a manual test. That's by hand, which is the fastest, and the recovery rate was about 71%. But if we compare it to our device, which is 63%, which was kind of in the range.
So other question? And you can see, I think it looks like the
It's completely
fish plate
on the other side.
Let's take this group.